In the last video, we had a box on an incline, and we looked at what was the net force acting on that box. In this video, what we're going to do is we're going to take that same box that was on the incline, but we're going to attach it to another box using this pulley system, and we're going to see how that affects all the forces acting on this object. So for now, we're going to say that this pulley is a massless pulley, and really that means just ignore it for now. This is going to come into handy later when the pulley does have mass in later chapters that will actually affect the forces acting on these objects. But for now, whenever you see massless pulley, that just means ignore the pulley and just try to figure out what the net forces are. All right, so let's do that. So we actually have two objects, right, that are moving in this situation. We have the first box and the second box. So we're going to actually, the first step is to draw all the forces acting, and there we go. We're going to draw all the forces acting on each box. So first let's do box 1, and then we'll do box 2 later on. So first let's do box 1. So what are all the forces? And there's really 4 forces you want to consider: gravity, friction, tension, and normal force. So let's go one at a time. So you know gravity is going to go straight down no matter what surface you're on. So even if you're at this incline, or you're upside down, it doesn't matter. Gravity always pushes straight down. So that's nice. You can get that out of the way. The next force you want to do is this is in contact with this surface, so that's going to exert a normal force perpendicular to this surface. So you have a normal force going like that. And really the normal force is kind of what's keeping this box from not sinking into the incline, and it's keeping it on this hill. The next force would be friction, and friction is always opposite to the direction of motion. So it tells you in the problem that you're kind of moving downwards like this, which you can kind of assume since you have a 60 kilogram box here and this is only 20 kilograms. It makes sense that you'd be falling like this. So since your box 1, your first box, wants to go to the right, that means friction is going to act to the left. All right? So it's always exactly opposite to your direction of motion. And the last force you want to check for is tension. And tension is any force that is exerted from a string or a rope. So clearly this rope right here is pulling box 1 to the right. So you can say, hey, there is a tension force pulling this box to the right. All right, so this is a great problem that has all 4 of our forces. Now let's go to box 2 really quick. In box 2, what forces do you have? Well, again, gravity pretty much acts on everything. Not pretty much, it 100% acts on everything, so you can always assume there's gravity. There is no contact with any surface. It's not in contact with the floor or the wall or anything, so there's actually no normal forces acting on box 2. There's also no friction by default because you're not in contact with any surface, so there's no friction. So your last thing is this string that's pulling you up that is going to exert a force of tension. Okay? Now, a lot of times people ask, does this force of tension over here equal the same force of tension pulling it up? And we're going to see later on that it actually doesn't, but since we have a massless pulley, we just assume, or not we assume, if the pulley is massless, then actually the tension is the same. Because if it's a massless pulley, you can kind of just imagine it's all connected by one string. So short answer to that question is yes, your tension forces are the same, even though you're on different objects. Later on that might not be true, but for now it is whenever you have a massless pulley. All right, so these are your forces. So the first step is to always draw all your forces. The next step is any force that is two-dimensional, you want to break into x and y. So what are our two-dimensional forces over here? Well, force of gravity is running entirely in the y direction, but all 3 of these forces here are two-dimensional, right? Normal force is going off at an angle, this is also going off at an angle, and this is also going off at an angle. All 3 of these are not entirely in the x direction or in the y direction. So ideally, so initially you might be tempted to just break each of these down into its x and y components. But as I showed in the last video, you can actually rotate your axes. Okay, so you don't have to say that this is your y-axis and this is your x-axis. You can actually rotate it. So you can say this is my x-axis and this is my y-axis. And if this is a little bit confusing right now, check out my last video where I go into a lot of detail about this. All right, but you can rotate your axis, so now this is your new x-axis and this is your new y-axis, which means all three of these forces are now one-dimensional forces, right? They're either entirely in the y direction or in the x direction. So that means that force of gravity is actually a two-dimensional force, which we can now split into its y component and its x component. So we can say this is its y component and this is its x component. All right, great. And on this side, so for box 2, everything's in the y direction. And a common question is, well, if I rotate the axis here, do I have to keep that same axis over here? And the answer is actually no. So in this problem, I'm going to stick with my traditional x and y axis. I'm going to say this is my x-axis and this is my y-axis. Y is going up and down, x is going left to right, which is what we normally think of. But here, I'm going to rotate it. And you can do that because you are looking at completely separate objects and you're treating them as completely separate beings with forces acting on them separately. So really, when you're looking at forces with two different objects, I'm going to put this metaphorical wall here. Okay, so here's your wall, and you really can just treat them. That looks a little messy. I'm going to get rid of that, but you get my point. That treat them completely separate. So here you can have x and y this way, and here you can have x and y looking like this, and that's totally fine. The math works out great at the end. All right. So step 1, draw all your forces. Step 2, anything two-dimensional, break it down into x and y. This is our only two-dimensional force. Here, everything is in the y direction, so you're good. Next step is to add up all your forces in x and y. So let's do that. So here is my forces in x, and here's my forces in y. So what forces do I, actually let me bring that down a little lower. Forces in y. All right. So what are the forces in the x direction? Well, I have a tension pulling this box 1 in the x direction to the right. So that is my first force that is in the x direction. And since it's pulling it to the right, I can say that it is positive. So, and remember, anything going to the right is a positive, is given a positive value. So that is positive force of tension. Friction, on the other hand, is pulling it to the left. So I'm going to subtract force of friction because anything going to the left is given a negative value in physics. What else do I have? I also have the x component of the force of gravity also pushing to the left. So when I say what are all the forces in the x direction, that means look what's pushing this object to the right or to the left along this new x-axis, okay? And this is it. This is pushing to the right, this is pushing to the left. So it sounds very fancy along the x-axis. You know, we make it dramatic, but really it's saying what's pushing me to the right and left, and I'm going to add them up. And when I add them up, I'm going to get the net forces in the x direction, right? If tension is pulling really hard and these two are not pushing as hard, then the box is going to go to the right. And if friction is pushing really hard, then it's going to go to the left. So it's really, in that sense, kind of intuitive, I believe. So anyways, you have force of gravity in the x pushing to the left. So I'm going to add force of gravity in the x going to the left. And like I showed in the last video, you might be tempted to put the negative sign here, which is totally, which is one way of doing it. But this number, when you calculate this number, you're actually going to get a negative number by default. So you don't want to make this negative right now. But we know that this needs to be a negative quantity eventually when we put in our numbers. Okay, so we'll come back to this right here, but and if this confuses you, I'll show you in the calculations in a second. So for now, I'm just going to add it. So if I have tension, I have friction, and I have force due to gravity in the x, that's going to be my overall kind of net force in the x direction. So that's my net force in the x direction. And since we are moving in the x direction, that means the overall net force in the x direction is mass times acceleration, okay? Because we are moving in the x direction, so there is an acceleration. In the y direction, you have a normal force pulling up. You have a force due to gravity pulling down, so therefore we expect this to be a negative quantity eventually, but I'm going to add it for now, and this is going to equal 0 because you are not accelerating in the y direction, right? Your net forces in the y direction is actually going to be 0. You're not moving in the y direction. If you were, even though you're moving along the x direction, if you were moving along the y direction, you would either fly off the incline or sink into it. So since you're not moving, your net force is going to have a 0 acceleration, which means you're going to have a 0 net force. Okay, before we even do this box here, I want to clarify. Let's just do this while we're at it. Okay, what are the x forces acting on this box? Well, there is nothing, right? Everything's pushing either up or down. So there's actually 0 forces acting in the x direction, so that's kind of nice. And then in the y direction, you have a tension pulling up. You have force due to gravity pulling down. And again, I'm just going to add it because, as I will show you, that when you're dealing with force of gravity, or force of gravity comma x, or force of gravity comma y, you get a negative number by default. So since you get a negative number by default, you want to add it, because if you subtracted it, you would actually be subtracting a negative quantity, which would be addition. So we'll get there in a second. And then this is going to equal, it is going to be moving, right? In the y direction, this box 2 is actually going to be moving down, so you know it's going to have an overall net force, so it's going to have a mass times an acceleration as well. So it is moving in this direction, so there is a net force. Now, before we actually move on, there's one thing you want to check whenever you have two objects, and that is, are your accelerations the same for box 1 and box 2? Because the way we wrote it right now, we're claiming that they're the same accelerations, right? We're saying MA and MA. So maybe we should specify this is definitely a different mass. This is M1 and we're talking about M2. So that's a good thing to specify. But what about the acceleration? Are box 1 and box 2 accelerating at the same rate? And the answer to that question is a little tricky. I would say it's yes and no. So let me explain what I mean. So the first part is yes, right? Essentially, they are accelerating at the same rate because they're both connected by a string. So if box 2 is accelerating really, really fast, box 1 is kind of stuck to box 2 and has no choice but to accelerate at the same rate, right? It's like if two people are attached to each other by a string and I run really, really quickly, my friend has no choice but to run at that exact same rate. So the answer is yes, that they do have the same acceleration, but the problem is that their directions are different. So why are their directions different? Well, box 1 is accelerating to the right, and anything to the right has a positive number to it. Whereas box 2 is accelerating down, which means it's a negative quantity. So the answer to our question is they are accelerating at the same value, at the same magnitude, but since their directions are different, they're actually, the correct answer is no, they have different accelerations. So actually this is going to be A1 and this is going to be A2. They are different accelerations because if something's positive and something's negative, they're clearly different things, okay? So the answer is actually they are different. But when we say they're different, right, we just said that, yeah, okay, they are different, but they're so similar, right? I mean, there's got to be a way we can resolve this issue. So this is how you resolve it. Well, you'll say, look, A1 really is the same as A2. The only difference is that one's positive and one's negative. So therefore, A1 equals, you can say, negative A2, right? Because no matter what A2 is, if you just take the opposite sign, you will get A1. Or you could say negative A1 equals A2. It doesn't matter, because both of these equations are saying, look, that no matter what this number is, take the opposite sign and you get this number. So let's just go back to our top one. So that's nice. So we're saying, look, they're different, A1 and A2, but really they're very, very similar. A1 is the same as A2 except for its sign, so A1 equals negative A2. And now we can just plug that in anywhere. So why don't we plug this one in here? So we can now we can rewrite this, and we can say that tension plus force due to gravity equals m2 times negative A1. Okay, because A2 is going to equal negative A1. All right, and that little negative sign there is going to make a huge difference. So this is a huge theme. Whenever you are dealing with two objects, check to see. So let's write this out in words. So theme. Whenever you have two objects, check if your accelerations are the same or if they are different. Okay? And you can sometimes have the same acceleration. There are problems where you could have something accelerate to the, well, I'll show you in a future video, but you can actually, there are times when you can have the same acceleration. Usually they'll make it different because that makes a great test problem, right? So if your teacher's trying to be tough, they will make it different. So always check when you have two objects, are the accelerations the same or are they going to be different? Great. Let's go back. So now we've kind of done all our steps, and now it's time to just plug in numbers. So let's start, like I showed in the last video. It's a good idea to start on the y side instead of x, because once you solve the normal force, you can get friction, and because friction's formula is mu times normal force. So let's just go ahead and plug in numbers. So first let's do the force due to gravity in the y and x. So we know if this is 30 here, that means this is 30 over here. And now we can say that the sine of 30 equals opposite, which is force due to gravity in the x direction. So the x component of force due to gravity divided by the hypotenuse, which is this blue line here, and that's just force due to gravity. That's that. And if we take cosine, then we can say, I can say cosine of 30 equals the adjacent side, so force of gravity in the y, divided by force of gravity. Okay, so for force of gravity in the y, we can say normal force plus Fg cosine 30 equals 0. And what is force due to gravity? Well, force due to gravity is the mass of your object, which is 20 kilograms, times the acceleration due to gravity, which is negative 9.8, right? Negative 9.8. So since this ends up being a negative quantity, that's why I don't want to subtract it over here, because if I subtracted a negative number, I'm actually adding that value onto my overall forces. So that's why you kind of have to be careful with forces. So this time for friction, I subtracted it, but here I added it. And the big takeaway is if you're ever in doubt, you can always add it initially, and then just make sure when you plug in the numbers that you are getting a negative value if it's supposed to be negative, right? So here friction should be negative and Fgx should be negative, and Fgy is negative, and it's clear that we are getting an overall negative quantity. So you have normal force plus this negative Fgx equals 0. So I apologize. This is bizarre that you're adding initially and then you make sure it's negative. But that's why you kind of have to just think about this a little bit here. So once you do all that, you will get that your normal force, let me actually write it down here. Your normal force is, once you plug all this into your calculator, you will get normal force is 30.2. 30.2 newtons. And newtons is the unit for forces. Okay, now let's go back to the X side. So we have tension. We don't know what the tension is. That's actually one of the things we're trying to figure out up here in part B. What is friction? Well, friction is mu times the normal force. So actually, I'm going to save us some time. So friction, I'm just going to write it up here, is mu times normal force. So notice that the formula for friction depends on the material you're in, which is this coefficient of friction, so that'll always be given, and the normal force, which is a force in the y direction. So that's why I recommend figuring out the normal force first and then doing the x forces, because you'll need that right here. So what is mu? Well, mu is 0.1. They tell you right there. 0.1. And normal force is 30.2. Great. And what is, and look, see, if you look at the formula for friction, right, you're going to always get a positive value inherently, because mu is always going to be a positive number, and normal force is always going to be a positive number because normal force is always pointing upwards. So therefore, you're always going to get a positive value. Therefore, if your friction is going to the left, you need to go and make it negative, because you need to say, hey, we're going to the left. Left means negative. On the other hand, the force due to gravity is always going to give you an inherently negative number, right? Because what is force due to gravity? Force due to gravity is mass times the acceleration due to gravity, which is always negative 9.8. So this is always giving you a negative number. So that's why when you're getting that negative number, you don't want to go and make it negative. So okay, so and again, I know this is confusing, but you always have to think, at the end of the day, as long as it ends up becoming negative, that's your goal, okay? So this is negative here, so I'm not going to make it negative. This one did not turn out negative, so I'm going to go and make it negative. And I know that's bizarre, because how can you just go and make things negative, right? We think of negative as an intrinsic property of numbers, but remember, in physics, negative just means direction. It just means we're going to the left or we're going down. So that's why you can just go and make things positive and negative, because you have to tell the problem which direction it's going. Okay, I think I've ranted enough on that. So let's keep going. So this is fg comma x, which is this here, fg sine of 30. And what is force due to gravity? Well, that's just the mass. That's just the mass, which is 20, times negative 9.8. Negative 9.8 times sine of 30. Sine of 30. And this equals m1, which is 20, times a1, and we don't know what the acceleration is. So I'm gonna box this, because this is important stuff that we just figured out here. All right. So this is pretty fun, right? I love physics. Oh my god. Anyways, so we are missing tension and acceleration. Okay, so we have two unknowns. So what am I going to do if I have two unknowns? Most likely there's another equation, which I can use. So that's why we have to do now this second object. So, but the second object, there's nothing in the x, so that's nice. So let's go to the y. In the y, we already said that tension plus force due to gravity equals m2 times negative a1. Again, tension, we don't know. Force due to gravity, well, what's the force due to gravity on box 2? It's the mass of box 2, which is 60, and again, the acceleration due to gravity is negative 9.8. Again, this is giving me a negative value, which is what I originally wanted. So what I recommend doing is, if you're going to add something that you expect to be, if you're going to, and I should have written this actually, Wait, did I do this right? Yes, I did this right. Okay, if you expect something to be negative, so this force due to gravity is going down. I expect it to be negative, but I'm adding it up here. Make a little mental note. Put a little side note saying, look, this should end up negative eventually. Okay, so yeah, so you have this tension plus this negative force due to gravity, and this equals m2, which is 60, times negative a1. All right. So let's box this because this is also good. So what I have here is another equation with two unknowns. So when you are doing problems with two objects, you generally will be left with two equations and two unknowns. That's just a common theme I've kind of noticed over the years. So when you have two equations and two unknowns, you can solve for each of these variables because you can solve for one variable and then plug it into the other. So let's solve for this one here. So what should we do? Let me just change that. Let's solve for tension. Why not? So you have tension equals, and then if you plug this into your calculator, you're going to get, this is 588. So this is negative 588, and I'm just adding it to the other side. So you have 588 minus 60 A1. Now I'm going to take this tension. So I'm going to solve for one variable. I solved for tension. And I'm going to take this and I'm going to plug it in right here. So if I take this and I plug it in here, I'm going to get one giant equation, but it's all going to have just one variable, right? It's going to have 588 minus 60A1 minus all these numbers equals 20A1. So there's only A1. So if I plug that in and I solve for A1, I'm going to spare you the troubles of putting in your calculator, and I'll just tell you the answer that A1 is 6.08. If I did my math right, this should be 6.08 meters per second squared. And does that make sense? Remember, every time you generate a value in physics, check doesn't make sense that it's positive or negative. So I got a positive number for A1, and that makes sense, right? We wrote up here that we expect box 1 to accelerate to the right, so it makes sense that it is positive. Cool. And once you figure out the acceleration, so we got that, and A2 is just going to be the same thing, but the negative value because it's going down. So what's part A? It's 6.08 meters per second squared for box 1, and negative 6.08 meters per second squared for box 2. What's part B? The force of tension. You just basically take this value, and now you're going to plug it in back here, and then you can solve for the force of tension. You could also plug it into this equation down here and get tension this way. And when you do that, again, this is just plug and chug. So I will tell you that the tension is equal to, let me see, the tension is equal to 200, again, this is if I did my math correctly, 233.4 newtons. All right. So big picture concepts, just to review, is whenever you have two objects, check if their accelerations are the same. This is where 90% of people kind of mess it up, and it's a very simple thing. It just, you have to remember to do it. So two objects means check if the accelerations are same or different. Usually they're different because that's what makes a harder problem. But if you notice, everything else followed the same exact principles.